Okay. Okay. So let me thank Prashant and the organizing committee first and foremost for inviting me for this talk. And so this is going to be a little bit of a pedagogical talk, mostly directed towards students. And this is a little older work done I mean, we did some experiments here, and some of the theory part we had done earlier with Prashant. So this will be basically studying entanglement in spin system, low dimensional spin system like spin chains. So introduction to quantum. So the plan of the talk is introduction to quantum spin system and spin qubits, entanglement in spin chains. Then detailed analysis to extract entanglement from the experimental data, magnetic susceptibility first, where we use magnetic susceptibility as an entanglement witness, and then variation of entanglement as a function of magnetic field, quantum phase transition. And then we also have specific heat as an entanglement witness, and that is actually we were the first to do that. So I don't have time, I think, for quantum discord. I'll go a little slow. So the idea is, with the advent of nanotechnology and other things, there is a miniaturization, and when you have miniaturization of these your bits, so it becomes faster because the time the electron takes to travel from one place to another in the circuit is small. So this is a current day chip, which is a nano kind of chip, and the smaller the chip, the faster it is. But with that, our problem is that we have also entered the nanometer. We have entered the quantum domain. So the classical transistors and all that were there will not work anymore, and we have to invoke quantum physics to study these things. So that is one angle to attack the problem. And of course, this is a little older photograph. I mean, I didn't update it. So here also we have reached the limit, like we have gone beyond 2020 now. So that is basically the classical limit completely fails in any electronic, in transistors or electronic chips. And coupled with that, I mean, it can be a problem, but it is also a blessing in disguise, because we have what we call the parallelism, quantum parallelism, which is facilitated by the quantum mechanics, inherent quantum mechanics in the system. So is the volume okay, or do I need to speak louder?
No, sir, it's fine, sir.
Fine. Okay. So now traditionally we had this classical bit, which had 0 or 1, which is captured by the voltage of a transistor or magnetization of ferromagnetic metal or intensity of pulse light. However, in quantum state, when we have qubits, which is quantum bits, which is the system can be in a superposition of the two states, which is basically both 0 and 1 and represented in a ket form, and where 0 and 1 are orthogonal to each other. So the inner product is 0. And it can be a two-level system, any two-level system, which can be captured by a variety of systems. It could be spin half, it could be polarization of a photon, it could be a charge state of a qubit of a superconducting and then or even a quantum dot, and or even atom, two-level, the ground state and excited state of an atom. So now you have a variety of qubit candidates, and since this is an experimental talk, I thought that I'll give a bit of an overview of various systems. So we have a photon, so basically linear polarization, where you have horizontal and vertical, circular polarization, where you have red circular polarizer, light circular polarizer. They have to be orthogonal. That is the criteria. So they form basically the basis of a Hilbert space. And nucleus spin up and down, electron spin up and down. Two-level atom, Josephson junction, then superconducting loop. So a variety of things. I have put this electron spin as red because this is what we are going to use in this talk. So you are all familiar probably with the block sphere representation, but that let me just quickly go through it. So that in the purest state, in the pure state, it is given by this. Okay, where this is the amplitude of 0 and this is the amplitude of 1. These are the two orthogonal state, again ground state of or excited state or spin up or spin down of an electron, and that is captured by 0 and 1, and it could be spin up and spin down also, and it is a qubit is represented on a block sphere with theta being the angle from the drawn from the positive z-axis, and phi is the azimuthal angle from the x-axis. And for mixed state, it is captured by a density matrix, which is 1 by 2 identity plus r dot sigma. Sigma are the polyspin matrices, and the ri's. So it's a 3 component because x, y, and z. So ri, which is I equal to x, y, z, or 1, 2, 3. So the value of ri is given as expectation value of the sigma, or basically trace of rho times sigma I. So now this is for one level system. Now if we have, sorry, this is for 1 qubit system. If we have more than 1 qubit, we can write them. So if you have 2 spin system, we can write them as 0, 0, 0, 1, 1, 0, and 1, 1. This is the Hilbert space dimension increases to 4. And if I have 0 equal to 1, which is basically 1, 0, and 1 is a 0 equal to up spin and 1 equal to down spin, which is represented by 0, 1, then so I can have a suitable superposition of these two states, of the product states. So these are product states of any two product state, and it can be formulated in such a way that I cannot write them as separable states. In the sense, I cannot write them as product states of qubits belonging to separate Hilbert space. So such a state is an entangled state, and it cannot be expressed as a direct product state. So this particular state is one of the best state called the singlet state, which will be extremely useful in this talk. Now, how do we quantify entanglement for a pure state? That is basically, if we take this, we formulate the density matrix, which is ket and bra, and that is a 4 by 4 matrix. And if we take the reduced density matrix, which is basically we trace out one of the degrees of freedom, let's say trace out over B, the Hilbert space of the B, you can consider them A and B, Alice and Bob kind of thing. And we have, after tracing out this state, which is basically to start with a pure state, we have a classical mixture. In this particular case, it is a perfect mixture, rather complete mixture. So equal probability of being up and down, and there are no orthogonal elements. And the entanglement, which is defined as a one-dimensional entropy, is taken as a trace of rho times log of a rho a. And since this is diagonal, so it will be very easy to calculate. And because we have the minus sign here, and that essentially makes the entanglement as a positive number, because we have half here, so logarithm of half will always be negative. So there is a negative sign. That's why we put a negative sign here, and the entanglement is 1. So that's the maximum entanglement that could be in a bipartite system. So now, so what are the main operations when you do the quantum computer? You do an input, basically. So basically, yeah. So first you do an initialization, which is like input, and then you do the manipulation, and then readout. So there's a DiVincenzo criteria which says that you must be able to characterize well-defined states, quantum states, to be used as qubits, which is basically initialization. Then prepare suitable states within the set. Carry out quantum evolution, that is the computation, which is the quantum gates, and avoid decoherence long enough to compute, and then read out the result. That's the DiVincenzo criteria for any quantum. So what are the challenges for making? Now, since I come from condensed matter background, so I will stick to the condensed matter applications here, not the optical or quantum optical one. So the challenges are, you have to make the synthesis where you have to have essentially inbuilt correlations and strong correlations where you have inherent entanglement in the system. Then, of course, you need to do experimental techniques where you integrate. So it has to be an integration of magnetic and optical techniques with nanotechnology, because you have to make miniature circuits, miniature components, because you need to isolate them, and for that you need nanotechnology. So these are the components that are essential for a particular for fabricating a quantum computer. So this is just an example. So supposing there are 2 spins, and they could be in the ground state and excited state. And when we have, so these are in a semiconductor, let's say silicon, and we have this doping, so doped elements could be a variety of things. Could be bismuth, could be phosphorus, which are basically N-type, and they have this Rydberg state where you have basically. So if I so if I switch on a light, and put them in the excited state. So what happens in the excited state, they're more extended and there will be overlap. And most of the time, this overlap is basically anti-symmetric in the spin space, or you have antiferromagnetic interaction, and thereby you have entanglement in the system. So this is how you induce the entanglement. But there are some systems where you have natural entanglement, and these are low dimensional magnetic systems. And low dimensional as in like in both ways. Number one, the spin has to be low, better to work with spin half, because that's the most discrete system. And so that is the low spin system. And we also have a low dimensional system like spin chain or similar. And there are various models. You have Ising model, which is classical, but if you apply a transverse magnetic field in the Ising model, it becomes quantum. And the system that we are going to study is captured by Heisenberg model, which I'm going to describe here, which is inherently quantum because you have this sp2 symmetry in the system. So now you have this natural entanglement present in the system. So in many condensed matter system, you don't have to induce entanglement. There is already natural entanglement. You just have to harness it by cooling it below a particular temperature, or sometimes applying a transverse magnetic field. So the natural question to ask would be, how much of entanglement is there? Can we quantify it? How is it distributed in space? And can we use it for anything? So so you have this. So this is the transverse field Ising model. So this is a normal Ising model where the sigma z. So basically the spins are along the z. This is the quantization axis. Let's say sigma z, and you apply the magnetic field also along z axis. So in that case, or rather the Zeeman field also along the z axis. In such a case, the two terms of the Hamiltonian commute with each other. So basically, H commutes in absence of magnetic field. If you write H, commutes with the external magnetic field, and you don't have any non-trivial dynamics present in the system. However, in transverse field Ising matter, because sigma z and sigma x do not commute with each other, in such case, you have basically spin fluctuation in the system, and this can also like if you have a small field less than the critical field, then these two commute with each other, you have enhanced spin fluctuation. And if you go to very, very high field, then this will force all the spins to be along x-axis. In such a case, it's on the other side. And these two phases are separated by what you call a quantum phase condition. So this is our system. So what we have is, this is a Heisenberg antiferromagnetic alternating dimer system in the sense key. So these are the small crystals that in principle you can synthesize in the lab also. It's possible to buy, but we had very nice chemists in our institute who allowed us to use their facilities, and some of our students have made this crystal also. So this is copper nitrate, and if you ask me the structure, that I will not be able to tell. So the idea is you have these spins. Let's say this is spin 1, this is spin 2, this is spin 3, this is spin 4. Now the idea is like spin 1 and 2, or let's say this is 1, 2, 3 and 4, whatever, like, yeah. So 1 and 2 and 3 and 4 are coupled among themselves with a exchange called capital J. And spin 2 and 3 are coupled among themselves by a exchange which is small j. And capital J is much, much larger than small j. So the Hamiltonian is captured by S1 dot S2 plus J S2 dot S3. And then again, it will repeat. Like if I have S3 dot S4, it is the same as S1 dot S2. So in effect, the Hamiltonian can be summarized by this. And this is called an alternating dimer model. Okay. So a pure dimer will be when the small j is 0. So it's just one S1 dot S2. So these are dimers which are independent of each other. They don't couple with each other. But in order to have a many body system, it is better. So you have this weak coupling and you have a many body oxide. And you apply the magnetic field. So this is S1 dot S2. So you have a spherical symmetry. And this is isotropic Heisenberg model. So in anisotropy, what happens is, so S1 dot S2 effectively can be written as S1x, S2x, plus S1y, S2y, plus S1z, S2z. We will see in the next slides. But Ising system is only S1z, S2z. Okay. So you have a spherical symmetry here. and that is what is very important to give entanglement. So now this is the exchange couple model, and as I said that this can be actually captured by basically a 4-dimensional Hilbert space to start with, and so if you just take two spins here and spin half, so they can combine in the following way. Either they can be a singlet state between them, or they can be parallel to each other, which is a triplet state. So singlet and triplet state are separated by the, so here if I take Ji, so I is the same, like Ji is equal to J. So the exchange couple, the basically the gap, exchange gap is something like J. And if you have a magnetic field, so now what happens is, if there is a spin half here, they can combine to give spin 0, or they can combine to give spin 1. Now in the spin 1, which is the triplet state, so there the multiplicity is 3, and singlet state multiplicity is 1. So 2s plus 1 basically. So here s equal to 1, so 2s plus 1 is 3. So basically this red one is captured by the singlet state. This is if I take J is positive. Okay. So for antiferromagnetic ground state, the J is positive. So and these three among them, so basically, okay, so this is minus J, let's say, and this is, yeah. So this is the energy S and MS, and so basically this is 0, 1, 0, and this fellow is 1 minus 1. This fellow is 1, 1. Okay. So what happens is basically there is this spin gap. But if you go on increasing the field, so this is the ms equal to minus 1 state corresponding to s equal to 1. Sorry, ms equal to plus 1 state corresponding to s equal to 1. Ms equal to minus 1 is this one. So this goes and crosses over this state. So this is like a crossover or a quantum phase transition in a many-body system, thermodynamic system. So a bit about Heisenberg model continuing, because I presume that there is not much background on that. So I have the system, and you have the same thing which I had written down before. Now I'm labeling the states. So these are the states basically. So this is the s equal to 0 corresponding to, sorry, ms equal to 0 corresponding to s equal to 0. This is the s equal to 0 corresponding to, sorry, ms equal to 0 corresponding to s equal to 1. This is the ms equal to 1 corresponding to s equal to 1. ms equal to minus 1 corresponding to s equal to 1, as the case may be. And the singlet state. So now what happens is, in absence of any external magnetic field, these are the 4 states, and this is a non-degenerate state, and this is a 3-fold degenerate state in absence of any magnetic field. So there is now, if J is less than 0, then this will be ulta. So basically this will be the ground state, this will be the excited state. In such a case, the ground state would be the ferromagnetic state, and this is basically a separable state. This is also a separable state, so there is no entanglement in the ferromagnetic state. There is entanglement only when the system is antiferromagnetic, when the ground state is this singlet state. Okay, so there's a little bit of math. The same Hamiltonian is written in this form. Okay, so as I said, sigma 1x, sigma 2x, so sigma 1y, sigma 2y, sigma 1z, sigma 2z, and this part is captured by this. This can be worked out very easily. I do that in my classroom, and this is basically the Zeeman part. Okay, and if you add them, this is the Hamiltonian. Now this is a Hamiltonian which is in a block diagonal form, you can see, and one eigenvalue is j by 4 plus b, one eigenvalue is j by 4 minus b, and these are the eigenvalues corresponding to up and down. Okay, now when you diagonalize this 2 by 2 matrix, then what you get is, so basically, yeah, up is 1 0 0 0, where the eigenvalue is j by 4 plus b, and down is 0 0 0 1, and the eigenvalue is j by 4 minus b. When you diagonalize this Hamiltonian, then one of the eigenvectors is this, with the eigenvalue j by 4, which is the ms equal to 0 corresponding to s equal to 1, and the singlet state, which is the ground state, is this, where the eigenvalue is minus of 3j by 4. Okay, so one of these will be minus of 3j by 4, and that will be j by 4. And in absence of magnetic field, if I put b equal to 0, then all these three will be degenerate, threefold degenerate. So that's what I was talking about in the last slide. Okay. So this is just to capture one of the previous calculation. So basically, if I have the density matrix, overall density matrix, phi minus phi minus, phi minus is the singlet state. Then I have this system, and if I take the reduced density matrix, then I have this to be the maximally mixed density matrix, and this is the finite temperature. So basically, so this is zero temperature. Okay, zero temperature picture. Now, what happens is at finite temperature is that we have this thing which people might have studied in their quantum statistical mechanics course, is the thermal density matrix, where so I write down as e to the power minus of beta ei sum over ei ket ei bra. So yeah, so basically these are the ket bra things of all the four states, and this is the e to the power minus of beta e. So you remember the eigenvalues were j by 4 plus b, j by 4 minus b, j by 4 minus 3, j by 4, and that's what we write. Okay. So the density matrix is normalized by taking z equal to trace of rho and dividing by that. Now, so yeah, so up is this, down is this, phi plus is this, phi minus is this, and the rho is basically this. So it preserves the same structure which we had here. You see, so basically it's the block diagonal form. So and sorry, I should go one step back. Yeah, so this is the form. So block diagonal form, this, and this. So it's preserved the same structure, the density matrix also, and that is it's called the X type density matrices. And there is a very good paper by Wang and Zanardi where they discuss the properties of such a X type density matrix. Wang and Zanardi. So now what happens at very high temperature? So this is Prashant told me that this paper has become very popular at the conference or school, and so let me just go through this calculation a little bit. So at the highest temperature, which is basically yeah, beta goes to 0, the density matrix reduces to something like this. This can be written as, so 1 by 4 times this, plus 1 by 4 times this, plus 1 by 4 times this, plus 1 by 4 times this. Okay, this is a separable density matrix. Now I say that it is separable, but you may not agree with it. So let me explain why. Now this fellow can be written as 1001 tensor 1001. So a little bit of tensor product is needed to understand these things. And then you have this 0101 1001. So effectively, I wrote all the four terms as a product of, as a sum of product of two density matrices. Two means single qubit density matrices. They are all like density matrix, right? Because if you trace them, it is one. Okay. And another thing is, if you take the coefficients, all of them, 1 by 4, 1 by 4, 1 by 4, add them, it comes to be 1. So this is called a convex sum. Okay. So this is a property of algebra, which you can study in Segre-Lang algebra. Or no, so this is this is sorry, it's a little bit more involved. This is called Hahn-Banach separability theorem. It's a part of functional analysis, and any standard book will give you this. One second. Why is it stuck? Right. Okay. So rho is separable and can be expressed as a convex sum of tensor product of two subsystems. There exists pk, which is a coefficient which was 1 by 4 in our case for the four terms. Pk greater than or equal to 0 such that rho equal to sum over k pk rho 1k tensor rho 2k, where 1 and 2 are density matrix belonging to Hilbert space 1 and 2, and for sum over k, pk goes to 1. This is expressed as a convex sum. If not, then this cannot be expressed as a convex sum. Then the system may be entangled. Now, if you remember okay, let me go back to the Hamiltonian. So we had this like sigma 1 dot sigma 2 kind of thing, vector sigma 1 dot sigma 2, which is basically sigma 1x, sigma 2x, sigma 1y, sigma 2y, sigma 1z, sigma 2z, and addition of them. So that same term, like sigma 1 dot sigma 2 is basically this plus this plus this. If I take the now, so this is a correlation. Okay, this is the correlation which gives you the entanglement. If I have a perfectly separable system, then this can be written as sigma 1x, sigma 2x product, sigma 1y expectation value, sigma 2y, sigma 1, and each of them are 0 because polyspin matrices are traceless. Okay, so for a perfectly separable system, this correlation goes to 0. There is no entanglement. Here also we see how we defined that is a perfectly, so this is a perfectly separable state. That is because even though it is a mixed state, so for to basically capture the entanglement, we need to see whether it is separable or entangled. There are various measures. Now, to see whether it is separable or not, the measure is the convex sum, which we discussed, the convex sum. And if because of this property, from this property follows Perez-Horodoki criteria, negativity, and partial transposition. All of them follow from here. Okay. So, coming. Okay. So now this is for high temperature. So what about intermediate temperature? Low temperature, we have seen at the lowest temperature, what happens is the entire system is in the singlet state. We will see that in experimental data also. And the singlet state is maximally entangled, so the system is entangled. What happens in intermediate temperature? This is intermediate temperature. What happens in intermediate temperature is, supposing I take the internal energy definition is that it is the expectation value of the Hamiltonian, and the magnetization definition is that sigma I z sum over I 1 to n. All the spins are expectation value of all the spins are along z are added. So why I take along z? Because when I do the measurement, I have to apply an external magnetic field, small, even if it's small, to measure susceptibility, and that defines the quantization axis. And my external field is along that direction. That is the z direction, and that is where along that direction the magnetization is defined. Now sigma 1 dot sigma 2 expectation value, mod of expectation value is sigma 1x. It's the same thing. Now this is equal to this, and this is the triangular inequality or Cauchy-Schwarz inequality. This is always less than or equal to mod of sigma 1 mod of sigma 2. Now mod of sigma 1 mod of sigma 2 is 1. This is 1. This is the maximum value is 1. So it is always less than or equal to 1. Okay. Now, so you can imagine this. That let's say my system lies on the Hilbert on the Bloch sphere. So if I take the expectation value of the system which lies on the Bloch sphere, that will be 1. If it is lies lesser than the Bloch sphere, then it will be less than 1. Okay. And if it is completely at 0 at the center of the Bloch sphere, then it is 0. And that is what we saw in the completely separable state, that it is 0. So this is a way to understand this. So Hamiltonian is J, this thing. So now if I take the expectation value, okay. Now if I take the expectation value of this, then you see this definition, that is M, and expectation value of this is U. So I write U minus BM by NJ. There are n terms. So 1 by n, and this is summed over this term. So this has to be, so according to this, the Cauchy-Schwarz inequality has to be less than or equal to 1. Okay, less than or equal to 1. Therefore, U minus MJ has to be less than or equal to 1. But if it is, so that's the classical result. But if it is greater than 1, that means you have an entangled state, and therefore I can use this term as an entanglement witness. Okay, so that is what is entanglement witness. That is how it is defined. If it violates the Cauchy-Schwarz inequality, that means the system is entangled. Good. It's stuck. I don't know why. Not moving. Maybe I have to bring this. Okay. Right. So there is an entanglement witness called concurrence, which is which is defined as follows. This was given in Wooters. You will find the reference even in Prashant and our paper. That rho 1 2 tilde. So if you have a bipartite system, whose density matrix is rho 1, 2, you take a star. Now, in this particular case, it's a real, but in general, you take a star and you multiply by sigma 1 cross sigma 2 cross sigma 2 from both sides. So this is like you are doing a sort of time reversal operation. Okay. And so basically, like your partial transpose kind of a thing. And C is equal to, so concurrence is defined as, so now you find out the eigenvalues of this rho 1, 2. And if the eigenvalues of rho 1, 2 is lambda 1, lambda 2, lambda 3, lambda 4, and if you take the root of that, so if you arrange them in descending order, so lambda 1 is greater than lambda 2 is greater than lambda 3 is greater than lambda 4. In such a case, what will happen is that if you arrange them in descending order, then the root over lambda 1 minus root lambda 2 minus root lambda 3 minus root lambda 4 and 0, whichever is the maximum, gives me the concurrence. Now, if this term is negative, that means the concurrence is 0. This will be, concurrence will occur only when this term is positive. So this is given in this derivation is given in this paper. Now in ferromagnet, it is 0. Okay, it can be easily seen. Like I can basically write down sigma I dot sigma I class 1, which is the nearest neighbor, as, so this is basically in terms of the spin fluctuation term, and this is 2 sigma 3. It can be written as like that. And this term, if I take the expectation value of this term, then both sides are up, up. You see, this is a raising and lowering operator. Both sides are up, up. In such a case, you see, if I operate on this, this will be, operate on this and this, they will change. And what happens is one will lower, one will raise, the inner product will be 0. Or you can see this way, like this will lower, but this operating on up, it cannot go up, so this will give 0. So there is no another way to see that there is no spin fluctuation basically in ferromagnet. However, and also because SIZ commutes with the Hamiltonian. However, for an antiferromagnet, even in the absence of magnetic field, if you see, my definition was U minus Bm by Nj. Now I can put B equal to 0. So B is equal to 0 means U by Nj is greater than or equal to 1. This is when I don't apply any external magnetic field. And the concurrence, so Kohner and Wouters derived this. So the you remember, this is the entanglement witness. U by Nj has to be greater than 1. Only then you have an entanglement state. So basically that can be cast, so it's 0 and this term. Now only if this term is positive, you will have a concurrence. So same, so there's a half term here, and 0 U by Nj minus 1. Only when U by Nj is greater than 1, this is entangled. When this is less than 1, it is not entangled. So this is like an entangled witness. So let's see. I have calculated U by Nj. Okay, this was already given. For an isotropic system, and I'm not applying any external magnetic field, I have sigma 1x, sigma 2x, sigma 1y, sigma 2y, sigma 1z, sigma 2z to be same. Okay, so I can just replace the other terms. So basically, I can write 3 times one of them. And this is S1 dot S2 basically. So I cast this U by Nj minus 1 to be this. Okay, there's a 1 by 4. And S1 dot S2 can be evaluated. So I have done that. It is very easy. You have this very complicated density matrix, and we calculated that. So using this density matrix, I can calculate the S1 dot S2 times rho and take the trace over that, and that comes out to be this. That comes out to be this. Okay. So basically, I cast this fellow in this term, and I have C equal to 2 max 1 minus 0. 1 minus e to the power minus beta j by 1 plus 3 e to the power minus beta j. Okay, this is in the B equal to 0 limit. And so this is the formula, that C equal to this. And this was given by Vedral. And so susceptibility, okay, so susceptibility is defined as, so this is from the fluctuation dissipation theorem. Is defined as G square mu B square n. N is the total number of spins or Avogadro number of spins by kBt 1 by 4 plus this term S1 dot S2, which is a correlation, which is given here. You can derive that. So basically, and you invert this. Okay, so chi. So basically, C max, C equal to max 0, 1 minus 6 kBT x by g square mu square v n. So this is the, now this is our experimental data, magnetic susceptibility for this system, EMF per mole, and the region which is greater than this. So if you see this, so if this is negative, that means there is no entanglement. So if this is zero, if this is equal to 1, where it is 0, is the boundary, separable boundary, and that is where chi equal to this, and this is the boundary, separable regions. So basically, above that separable, below that is entanglement. Okay. So again, I put the same formula here. So I have, this is my data, let's say, okay, and magnetic susceptibility, and this is the calculated the susceptibility, free suspense susceptibility. So anything above this line is separable, and anything below this line is entanglement. So if I take a subtraction of these two, so basically here, so then C equal to, so concurrence is given by 0, 1 minus this thing. So if I subtract that from 1, so this is my data, and this is the fitted curve, this is the theoretical curve, and from data we get this entanglement. So basically, you see, now I could not go to very low temperature, with the minimum temperature was a little less than 2, basically 1.7, 1.8. So if, so the concurrence is coming out to be 0.8. Okay. For if I do the theory, then theoretical entanglement, so we regenerated the plot from this paper using the, so I can even use this formula, and for this particular Hamiltonian, I see, so this is the concurrence, this is the temperature curve, and this is the field. Okay, so if I am at zero field, so basically this, zero field is this, yeah. So if I am here, then I see that beyond this, so let's say 5, beyond 5, temperature 5, there is no entanglement, but below 5 entanglement starts, and this becomes like this, so it flattens out. So at zero temperature, at zero field, my entanglement is 1, which is a maximally entangled system. Okay, now another thing you notice, as I increase the temperature, so let's say as I increase the temperature here, so it goes like this, flat, right? And that is what we captured like this. If I lower the temperature further, then it will go like that and flatten out. Okay, right. And there is also a function of field, which I'm going to talk about later, but just see that it goes like that. Okay, so this is the experimental entanglement where okay, susceptibility defined as at zero temperature, at zero field, essentially field goes to 0. At field non-zero, there is something called generalized susceptibility. We calculated that, and the entanglement witness is captured in terms of magnetization and chi in the following way, and we generated this. This is the experimental entanglement as a function of field, and this is as a function of temperature at various fields. Okay, so there's a completely 3D plot that we experimentally generated. Okay, so right, so on one side is the experimental curve, and another side is the theoretical curve. Okay, the quality is a little bad. Yeah, so this is that theoretical entanglement. Now you see what happens as a function of magnetic field. So now what happens is, this is a magnetic field. So I had just reversed this thing a little bit so that you can see the magnetic field. So the entanglement goes like that. Even at zero temperature, entanglement going like that. Suddenly the entanglement drops at this particular field. Okay, so this is the field axis. This is the field axis. If I go on increasing the field, suddenly it drops to 0. Okay, at zero temperature. And in non-zero temperature, it will go something like this and flatten out like that. Okay, but still it drops. So this is what we observe in the entanglement work as a function of field. Okay, so one is the experimental curve, another theoretical curve. So this is at the lowest temperature, which is at 1.8 Kelvin, and the entanglement goes like that, and it drops to 0, towards 0. Okay, so at around 4 Kelvin or 5 Kelvin, it goes completely to 0. And why is that so? Because if you see, we come back to this curve. If I go on increasing the field, this state does not change. Okay, this state does not change. But this state, which is basically a separable state, this state becomes the ground state beyond a certain field. Let's say there's 4 Tesla or 3, whatever. And the new state is a separable state. And that's the reason why you see the new state. So basically, the entanglement gradually drops as you increase the field, and it goes to 0. Because at 0 temperature, the state is a singlet state. That's in 0 temperature and 0 field. And as you go on increasing the field, the system crosses over from a singlet state to a triplet, but separable triplets. So, and remember that there is no entanglement for ferromagnetic ground state. I had demonstrated earlier. So therefore, the system crosses over from entangled system to a non-entangled system, a separable system as a function of field. So this is what is called quantum phase transition. Now okay. I have 20 minutes left, less than 20 minutes left. We leave 5 minutes for questions, so 15 minutes left. So so we define quantum phase transition as if your Hamiltonian has a parameter g, h0 plus g h1, where h0 and h1 commute, but eigenfunctions are independent g even though the eigenvalues vary with g. So remember that we have eigenfunctions which are independent of the external magnetic field. Like if I just quickly go back. Yeah. So these are the eigenfunctions 1, 2, 3, and 4. They are not field dependent, but the eigenvalues are field dependent. So that's what it is saying that eigenfunctions are independent of g, even though the eigenvalues vary with g. So there is a level crossing where an excited state becomes the ground state at g equal to gc, creating a point of non-nullity. So we have this crossover. So therefore, so it could be either avoided level crossing or crossover. So that is what is happening. So basically, it's like a quantum phase transition that is happening here, and entanglement captures the quantum. Okay, so there is a very okay. Let me very quickly go through this. So this is also a part of our work, which we did based on Black-Ovetra's theoretical work. So there are, it's an important concept. So for product state, okay. So now chi, the average susceptibility can be chi x plus chi y chi z, which is greater than or equal to ns by kt. Now, the definition of chi, which is from the fluctuation dissipation theorem, which let me just quickly go back here. So this is the definition of chi. Can be written as, so this is the variance of the magnetization. So mi square minus mi square expectation value minus mi expectation value. That follows from the fluctuation dissipation theorem. And a very good reference is Kubo. And this is the variance of mi square, magnetization, and this is mi square minus mi expectation value square. So so basically this would be expressed as delta s x square, delta s y square, delta z square, sz square. So this is basically sx square, sy square, sz square expectation value minus of sx expectation value square, sy expectation value square, sz. So this is greater than or equal to s. This can be shown. So again, for separable state, these two will be 0. So that goes to 0. So effectively, this thing can be written as m square x delta square variance of mx, variance of my, variance of mz, and effectively it is si. So because mx is sum over I si, so I pull the sum outside, and this is what we get. So now remember, s square. What is s square? S square is s into s plus 1. Okay. So s into s plus 1 minus s square. So that is effectively, so s square gets cancelled and you have s. So that is ns by kt. Okay. So this is the variance. And if it is greater than that, then only it is entanglement. Okay. Now this m square is mx square plus m square plus mz square, which is less than or equal to m square n square s square, which is it follows from the fact that sigma x square plus sigma y square plus sigma z square is less than or equal to 1 for a single field. Okay. Only if it lies on the Bloch sphere, pure state, it is equal to. So basically, if I substitute that, so this turns out to be greater than or equal to ns plus 1 by ns m square, and therefore chi is equal to chi x plus chi y plus chi z is greater than or equal to ns by kt. I substitute in this and I get this. So therefore, I can formulate this as follows. So this 1 minus kt chi prime by ns plus m square by n square. So this captures the local property. This captures the local property. This captures the non-local property. Why it captures the non-local property? Because if I go to the last slide, because of this captures the correlation. Okay. Chi captures the non-local properties, and simply m square captures the local properties. So I can write, so I can combine these into this form 1 minus kt chi bar by ns plus m square by n square s square, and that's less than or equal to 1 follows from here. So this was derived, and this captures the non-local properties, this captures the local properties. Okay. Okay. So I have, so basically, this is the energy level diagram for a dimer, and this is for the alternating dimer, which is our system. So basically, this is a higher dimensional system, 16-dimensional system, and the magnetization goes like this. Okay, and this is the fit for a dimer system, but there's the blue line is the fit for an alternating dimer system. And the susceptibility, the susceptibility is theoretically actually. So I have derived this formula, and this is the generalized susceptibility where the field is also included. This goes like that. Okay, so the magnetization also goes like that, and the susceptibility goes like this. Okay, but our definition was, okay, so this is the generalized susceptibility. Now, so basically the data is like that, the theory curve is like that. That is because in the experimental data, so there is a slight change in the. So basically, this is basically the, okay. So Q as a function of field, and this is susceptibility. So Q as a function of field. So I have the Q which goes to 1 at the lowest field, it suddenly drops, and this is the magnetization P which goes as a magnetization which goes like that. Okay, so in between, if I plot Q plus P, this is the partial information sharing, is Q and P. If I plot Q plus P, so this is the Q, this is the P, and as I said, this is the experimental data, this is experimental, this is theory. So there should be a, so basically it goes like that, and there should be a dip somewhere in between. So this is at 0 temperature, the dip is very sharp, and as you go at higher temperature, it is slightly curvy. Okay, this is the P plus Q. This is reproduced from this paper by Blatko et al. Sorry, I forgot to cite it here. Yeah, reproduced from this paper. And my experimental data. So this is So this is the curve, the 3D plot which we reproduced. And you see, this is the 0 temperature where there's a sharp dip. But if you go to at higher temperature, there will be slight curvature here. Okay, and this is what the experimental data is. So basically, this is the dip here, and this is the sharp here. This is the dip at this temperature, which we this was at 1.8. Okay, this is the theory, this is the experimental, and that captures. So this is the quantum phase transition around 3.5 Tesla, where the quantum phase transition is happening. Now let me go to the last part, which is basically heat capacity and entanglement. I'll go a little fast here. Again, we were the first people to show this. So heat capacity is again defined as a variance of h square. This is the expectation value of h is the energy, internal energy, h square minus h square, h square expectation value minus h expectation value square. And the measure of entanglement, you remember this we derived in the last part, is this, where the U, the heat capacity can be defined as the, so basically internal energy is the, this is the definition, which is Ct as a function of T and U integrate. So this is my experimental data. And this this was carried out from at very low temperature, 0.3 Kelvin actually, and this was carried out at Philipp Gegenberg's group in Germany in Göttingen University. We don't have such a low temperature, and this is the heat capacity as a function of temperature, and that's the fit. The red one is the fit to the experimental data. Okay, and in this case, you see there will be a lattice part here, heat capacity, which is subtracted. So we only have the magnetic part here. This is at 0. Okay, only the magnetic part, and the heat capacity increases and comes down. And the reason is okay. So this is a field dependent heat capacity. So this is the 0 temperature, and this is as we increase the field at various fields. So 7 Tesla almost goes like that. So okay, so this was also given by them, but we had derived a different entanglement witness here also heat capacity, and this is the free spin one. This is that bound above which it is separable, below which it's entangled. So this is the definition that we took, heat capacity for entanglement witness, and what we did at 0 field, U minus Nj equal is greater than 1 is the entangled state, and U was evaluated by integrating the heat capacity. Sorry, this is actually yeah. So U is dc dt, and we did the integration. Sorry, the definition was here. U is integral dp dt, and we integrated it, and this is the value where this is equal to 1 U by Nj. So we plotted U by Nj, and below that, so if it is negative, then below 1, then it is non-entangled. If it is above, then it's entangled. And if I calculate U by Nj, this is the entanglement witness. This goes because we basically measure till 0.3 Kelvin, so it goes very close to 1. Okay, and it drops. So that is also the dropping that we saw when we extracted the data from the susceptibility. Okay. This is a theoretical bit. Let me skip a little bit. This is temperature and field dependence of internal energy. And what we saw that entanglement witness as so this is the entanglement as a function of temperature and field, and this is the entanglement at different field, okay, as a function of temperature. So at very high field, there is no entanglement, you can see, okay, and at the lowest temperature, lowest field, you have very nice curve. So if I were to take one of those sections where we basically take a particular particular temperature and we sweep the field, then it comes like that. So CV goes like that, comes down. So this is where, so this is the heat capacity, and then again goes up and falls to 0. This is where the quantum phase transition happens. So how do we explain this particular curve? So it comes in between and then again grows and falls down. So what happens is this is something called Schottky anomaly, and Schottky-like anomaly in a two-level system. Now, if we are at 0 magnetic field, let's say, I am applying so this is as a this is as a function of field. Sorry, yeah. So this is a function of field. So supposing I am at a particular temperature and I increase the field. Now what happens is in heat capacity, how do you measure it? You supply a little bit of heat and you see the change in temperature. Now if I am at this place and then I'm applying so supposing I'm at a finite temperature, so the finite temperature, it will be a mixture somewhere here, and as I go on increasing the field, what happens is this crossover takes place. Now heat capacity measures the amount of energy that requires from me to go, say, at 0 field from here to here. Then as I go on increasing the field, the energy required to go from here to here is minimal. Okay, and here the energy required is 0. So the heat capacity will drop, and that's why it is dropping here. Okay, at this particular field. And so then what happens is, as I cross over, then this is my new ground state. Heat capacity is as I increase the field from here to here. Sorry, as I increase the basically I have to supply energy from here to go to here to here. So therefore, again, it starts rising and then finally it will drop off. Okay, this is a theoretical curve of heat capacity. This is the experimental curve. And we see that if so this is at 0.8 Kelvin, the entanglement witness goes to 0. This is the theoretical curve, this is the experimental curve. I think I'm close to my time, so I'll stop here. So this is, suddenly you see the entanglement goes to 0 as a function of field, and that captures the quantum phase change entanglement across field. Okay. So, oh yeah, this is just a review article that Nature Physics had asked to write. And so basically, this paper had cited 5 of our papers. So this heat capacity work is also there. And therefore, Nature Physics had asked me to write basically a review kind of thing, I mean, on this, news and views. And this is long distance relationship. So in spin change, how you can see the entanglement from one place to the other. So this is the model of the alternating dimers. So these are the dimers which are weakly coupled. And this is the same thing as I said. So here I have changed the notation a bit. SA plus up, SA this thing. So these are the 3 things as a function of magnetic field. Okay. I think yeah, I'll end up. I did not talk about quantum discord. There was no time. But so the antiferrometric ground state of a quantum mechanical system is entangled. Magnetic circuit can be used as a macroscopic entanglement witness using quantum mechanical uncertainty principle, which is P plus Q thing which I mentioned. One, it's possible to capture the quantum phase transition close to quantum critical point, and space heat capacity measurements at low temperature explicitly capture the QPT, and heat capacity can be used as an entanglement witness also. So I'd like to acknowledge a lot of my students. Thank you very much. So let me stop presenting, and I see the audience. Yeah.
Thank you, sir. Any question from the audience?
Hi. Hello.
Yeah.
So I had a question. So when you say antiferromagnetic, means
antiparamagnetic.
Yes, sir. So it is antiferromagnetic.
Antiferromagnetic. I say antiferromagnetic, not antiparamagnetic.
Yes.
There is no such thing as antiparamagnetic. Yeah, antiferromagnetic. Yeah.
So it is antiferromagnetic in a particular direction. Like let's say
what? Once again. Antiferromagnetic in a particular
direction.
For these kind of system, when you have a singlet state, you have this symmetry, SU2 symmetry, which can be mapped to O3 or kind of thing. So basically, spherical rotational symmetry. So it's not a particular direction.
So all the spins are antiferromagnetic in any direction.
Yeah. So the strictly speaking, directional antiferromagnetism comes in terms of when you study Ising model, whether you have a single anisotropy, you have a anisotropy axis. These are Heisenberg systems are isotropic. So as I said, so in single one of the properties of singlet state is as follows. So if I take up down minus down up, that is same as plus minus 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 plus. Okay, any direction you take, you can write down the singlet state. Okay, so singlet state is something which is isotropic or rotationally invariant. That's what he said. Is that clear?
Yes.
So up down minus down up is also equal to, so 0 1 minus 1 0 is also equal to plus minus 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 plus. Okay, plus minus is the basis for sigma x. Okay.
So basically, if we make a measurement, then we find that all spins are in one particular direction.
When it is 0, the spin is 0, then there is no particular, I mean, when the magnetization is 0, like at the lowest temperature, the magnetization goes to 0. So at that time, you cannot distinguish. Okay. Only when you apply a significantly higher magnetic field, then you are forcing them. So that is what was quantum phase transition. Basically, you are forcing them to be along a particular direction, and you are forcing them to be up, both up. So that's where the crossover goes. When you apply magnetic field, it crosses over from spherically symmetric to a particular direction. Any more question?
See, Chiranjib.
Yes.
Recently, there was some talks about using quantum Fisher information. Have you sort of kept track of it? Huh?
Yeah, I haven't included that yet. Yeah, I have, but point is that I'm not so much working in this now.
Okay.
Now I'm mostly
Okay.
into a nitrogen vacancy center. But yeah, so yeah, what's her name? Dipshika did some
That's
work.
right. That's right. That's right. Yeah.
She cited us, but she
Ah.
she didn't cite all our papers. One paper
Okay.
she cited. Then I told her we have a variety of papers, so please. So I said that yeah, next time we'll do that.
Okay. Okay. Good. Good. Yeah.
Yeah. So, hi, Chiranjib. I have a question for Mr. From It's a very nice talk. I understood quite a
Thank
lot.
you.
So the data you showed about susceptibility and the phase.
Can you speak a little louder? Can't hear. Yeah.
Yeah. Can you hear me now?
Yeah.
Yeah. I'm saying that the data you showed for phase transition, phase transition, and other things, that for the isotropic uniform case, XSZ case, or the dimerized XSZ case?
When we have, so it is going from one to the other. So the thing is, it is strictly speaking, like I did the analysis, did the maths for a dimer system, so that we can understand them better. It's just 4-dimensional Hilbert space. But strictly speaking, it's actually the lower the temperature you go, it can be shown. There is the Fisher, Bonner and Fisher had shown, the function is that the Michael Fisher actually, they had shown long time ago that the lower the temperature you go, the more the system becomes, you have more spins coming into the picture. Okay, so at higher temperature you can just do it with 2 spins, but at lower thing, all these dimers are coupled with each other, so it is basically many body ground state. So that's why you can say that this is a quantum phase transition. Otherwise you would say just a crossover.
No, I mean, my question is related to this dimerized XXZ model. So when you dimerize the system, then one can get topological signatures also.
So there are, so topological signatures can be seen. It has been seen. People have done neutron scattering experiments, and I'm forgetting the name. Bernd Keimer, I think. Yeah. So their group in Germany, they have done, and some people in Gabriel Appli also has done. So yeah, they do have this topological delocalization and all, which is basically the synthils, that nature paper. Those things have been observed. And when you go from singlet to triplet, so basically you have these triplons, condensate. You see a Bose-Einstein condensate, but that can be studied from neutron scattering kind of experiments. People have done that. There are
from your entanglement measure or concurrence, can one see the signatures of topological transition in this kind of chains, spin chains?
You need slightly different sample. So for this sample, we cannot see, and also you need to go to very low temperature, even lower temperature. So basically, as close to 0 as possible. So we cannot do that. Yes.
Yes. Okay. Because recently we studied this model, dimerized XXZ model, where we investigated the ground state properties.
Yeah, and in fact, Ujjwal and Aditya had also studied that, and they had cited our work also. So they did something similar sometime back. Yeah, Prashant will know their work. Yeah.
I see.
So Prashant, you're still there?